Hello everyone, this is Group 7, the Eaton Dexterous Robotics. I'm Ben Schreiner in Robotics Engineering Technology.
I am John Game in Electrical Engineering Technology.
I'm Halai Valu Patterson in Robotics Engineering Technology.
I am Aaron Neiman in Robotics Engineering Technology.
Currently, there exists no standard for the application of five-finger robotic end effectors or a robotic hand within an assembly line environment. Our project's aim was to demonstrate the viability of integrating a robotic hand into assembly lines, working alongside human operators. While Eaton employs a variety of robotic arms in their current assembly operations, these do not include robotic hands collaboratively working with humans. Our original objective was to deploy a robotic hand taking over the place of a human worker. This solution needed to match or exceed the efficiency of human labor. It was essential that the solution was capable of utilizing hand tools with the same proficiency as a human worker. This initial scope did not come to fruition as the addition of teleoperation was placed in the project at the beginning of the second semester. While we did not fully complete the entire scope of work, we did see massive success in the development of a proof of concept.
Our project has developed significantly over a year of work. Let's start at the beginning. In this video, we can see one of our first demonstrations of robotic arm movement with the five-finger hand. Very visibly, the arm is sluggish and slow to input responses. Additionally, the movement required a manual operator using rudimentary controls. In this next video, the hand makes an OK sign, proving great mobility and precision. Though this is good, the hand is rather sluggish and required manually manipulated keyframes that required massive amounts of time to set up.
With time and effort, lots of progress has been made since the beginning of testing. Let's take a look at where we are now. For our first demonstration, we were able to combine two of the three main sections of this project. The glove's positional data moves the position of the robotic arm, and the glove's fingers' positional data moves the position of the robotic fingers. Both the arm and the hand can move faster on their own, but we show relative caution while using them together. For our second demonstration, we have the force sensor at the end of the robotic fingers providing haptic feedback to the tips of the gloves. The screen here shows the individual sensors being activated. Here, you can see the reaction of fellow students feeling the force feedback for the first time. For our final demonstration, we have our newest fist bump. The project's progress is very visible from these demonstrations. The robotic arm and hand are able to work together at the same time with rapid response times and no need for keyframe setup.
This project was not without lessons to be learned. One of our first stops was with tackling the scale of this project. We found out after time that it is important to split large projects into smaller, well-defined chunks that one or two people can tackle on their own. With this, having multiple people work on the same part in the vein of rubber ducking can help lead to faster and less frustrating development, as one person can see what another might not. Additionally, since our scope has changed in the middle of our timeline, our project had to rapidly change as well. While we were able to do well and come out with a good proof of concept, it is always still important to check on project additions for potential scope creep.
Thank you to our mentors and partners at Purdue, Eaton, Sarcomere Dynamics, Haptics, and Touch Labs. Your help made this project possible.